particular reduction angle, this reduction identity works for the sine function? Can I change things a little bit? You guys meant this, didn't you? So, employing integration by parts, I got to split the sine to the nth of x into a u times dv. Now, whoever put this on the board, I agree with this for one reason. It's easy to anti-differentiate. And if you can't read it, that means the number of factors left over here are going to be n minus 1 of them. Now, just paying the consequence of my actions for this assignment of u and dv, I think differentiating u, ooh, we got it. Anti-differentiate over here, I agree with your signs. It's just that, excuse me, my goodness. Putting this all together, let me rewrite to make a full sentence. I think this implies that the integral of the sine to this power of x with respect to x is equal to the product of my u and my v minus the integral of my v du, which in this case is, can I slide over a little bit? Mm-hmm. Which in this case has a coefficient, which is n minus 1 that's negative, times the integral of, you guys, I don't agree with this. Did we differentiate correctly?
No.
Yeah, I think there's a problem over here. I think if I were to differentiate correctly, I would say that du is, well, let's wrap our fingers around this one.
N minus 1 times cosine of
times
Sine.
sine to the
oh yeah, sine to the
one
n
less power.
minus 2 times cosine of n minus 1, or to the n minus 1.
Well, 1 less, n minus 2.
Okay.
Oh, the blood's rushing out of my arms. I can't hear you. I can't hear
Dx.
you. Cosine x dx.
Yeah.
Chain rule. I got to multiply by the inside's derivative. I got to multiply by the derivative. What the heck was raised to the n minus 1 power? Did you guys see it?
Yeah.
That being the case, now I can finish this up. I think that means that sine the n of x in the integral is a product of my uv, got it, minus the integral of my v du, I pulled out my coefficient, and I think what's left over is the sine, it's n minus 2 of x, times the cosine of x dx. What do you think? What do you think? Yeah, I missed a factor, cosine of x, didn't I? So I guess I better come back in here and slip in one more factor. However, I think that implies that this original integral I was trying to evaluate is, okay, some garbage here. Who cares about this garbage? It's not an integral, right? It's just an algebra, a trigonometric expression. I think what's at issue is that I got to evaluate this integral, I think. Or actually, maybe not. Maybe I can get away with not evaluating it. Technically speaking, I think when it comes to the cosine squared of x, if I so choose, can't I interpret that as this? Do you think it's going to help?
Yes.
I think it is. I think it is because when I remove parentheses, I get to separate this one integral into two integrals. One of which will involve sine to the n of x dx, which is exactly what it started with. Let's give it a shot. Continuing to simplify the right-hand side, particularly that last one integral on the right-hand side, I'm left with this. You guys hear me? Is that okay? Because if it is, if I now take this one integral right here and add it to both sides of the equation, it cancels on the right-hand side. Equal sign, it's just the left-hand side. I get a total of, is that n of them? Oh, look at that. I think we're there. Well, I missed one step, the final step, which is divide both sides by n. and we get exactly what we have up there for the reduction formula. But you guys see I cheated? Once I applied integration by parts, right here, I massaged the integrand in such a way that I ended up with another integral that looked just like what I started with, neglecting, of course, a numerical coefficient out front. Be honest, is that okay? Is there anything from the homework you want to take a peek at?
Can you, I know you showed us this yesterday, but can you quickly show us how, I think it's 1 minus cosine of 2 theta equals, I think, 2 sine squared of theta?
Yes.
All right.
But if I'm going to show you how to do this,
Yeah.
you have to tell me if I'm backing up far enough. I might have to back up even farther.
Okay.
So humor me and be honest.
Okay.
Yes, sir.
Did you answer question from homework 7.1 yesterday?
Hope I did. But if I didn't, you can ask more today. It doesn't have to be over last night's homework.
Depressed.
Yeah.
Oh, was that it? You know, I have to confess, yesterday in class, first time ever, I gave an exam back and there were no questions. By the way, you guys, last night I didn't finish work till 10 o'clock. I'm on a committee that just started giving me lots and lots of work to read all night long. And so I did not go home last night and type up the solutions to the exam. I did go to my computer, I scanned it, I got a PDF file. I've just been too busy this morning to put it online. I promise after class, sometime this afternoon, I'll put it online before I leave campus, okay? You asked me to just give the answer solutions. Actually, I just took my notes, even though they're kind of sloppy, by hand, and I just converted it to PDF files, so you got everything worked out. Perfect. You guys just got to give me a little time after class in case I have people attacking me for questions. I just lost a question. Oh,
Yeah.
I'm sorry. Bradley, I'm serious.
Okay.
Dude, this is too important. Tell me if I'm just taking this out of thin air.
No, I remember that.
Because you guys, I think at this level of education, I really do expect you guys to be able to drive this one out of thin air. All right. However, I think this implies that if I simply replace this y with an x, then x plus x can be interpreted this way. But remember, I'm replacing y with an x. I think my first term becomes cosine squared of x. My second term, replacing y with x consistently, becomes sine squared of x. Actually, to be honest with you, this really is one version of my double angle identity for the cosine function. I think another one could be generated by diving in and simply replacing sine squared of x. I said replacing sine squared of x with 1 minus cosine squared of x, just via my Pythagorean identity. And if you guys allow me to remove parentheses and collect like terms on the right-hand side, I think that leaves me with this. Ah, shoot, that's kind of nice. I think the original double angle identity I created involves sines and cosines, but check out this version. It simply involves cosines alone on the right-hand side. That's kind of nice. Second version of my double angle identity for the cosine function. Come back up here. If instead I replace cosine squared of x with another name involving only sine squared, that would be this. Via, yet again, my Pythagorean identity. This time, however, I do think the set of parentheses on the right-hand side of the equal sign are superfluous. So let me just commit to combining like terms and check this out. Yet again, another third version of my double angle identity function for the cosine function. I can add. Thank you. Oh, you trust me. The further you study math, the worse you're going to be with arithmetic. And you guys, let me take a peek at, I don't know, how about the middle checked one? Can I erase this? Rewriting the middle checked one. Goodness, who did this? I have the cosine of 2x being equal to 2 cosine squared of x minus 1. You guys allow me just to isolate cosine squared of x. I'll add one to both sides. I'll divide both sides by 2. Ah, shoot. There's my nifty little reduction identity for replacing cosine squared of x with an expression involving a cosine expression raised to only the first power. The downside? The input gets more nasty, but the upside, the exponent is 1. Who really cares? Well, you and I do, because if I have a cosine squared factor in the Lagrange position, if I so choose, I can replace it with this expression, and if that's the only factor in the Lagrange position, then jeepers, I can anti-differentiate this mess piece of cake. Maybe a slight, tiny, small use of my head, replacing 2x with a u, but that's a piece of cake, I think. Are you being honest? Is that okay?
Yeah, definitely.
And I could have just easily taken this one right here, isolate the sine squared of x. The only thing that changes is I get a sign change in front of the cosine of 2x. That second term in the numerator's position. That's the only thing that changes. But you guys, this is a math class. Just ask. I shouldn't say anything that I can't justify.
How do we know,
Yes, sir.
how do you prove the top one though? That's like where you started from, but how do you get to there?
Oh,
Putting
this is
X and
so
Y
beautiful.
on?
You relax. Kick your feet up. I'll do all the work. So x-axis, y-axis, unit circle. Angle alpha. Just be honest with me. Is it okay if I interpret this point right here as being the point on the circle associated with alpha radians? Okay, now don't you stall. Don't stall. What are its coordinates? Ah, you're killing me. You stalled. You gone.
How do we know?
You do know.
Oh.
Cosine alpha?
It's such a nice purple pen is drying out.
Cosine alpha sine.
I heard that.
Oh, okay.
Sorry, I'm slow. And if I consider an angle in standard position associated with beta radians, don't you guys agree that the coordinates of this point right here is associated with the point in the circle with beta radians? Don't you think its coordinates are going to be these? Everybody?
Yeah.
That being the case, I think the distance between these 2 points is, well, some distance, whatever it is. By the way, what can you say about this green angle? What's its measure?
Minus beta?
I agree with that. Yes or no answer. Is alpha minus beta in green in standard position? No, it's not. But if you guys allow me to take that angle in green, alpha minus beta, if you allow me to just rotate it in the clockwise direction, beta radians, what do I get this? X-axis, y-axis, unit circle, in green. Here's my angle. In standard position, whose measures alpha minus beta. Like in my first picture, but in standard position. And I think here's a point in a circle associated with alpha minus beta radians, whose coordinates are blindly, no thinking, the cosine of that angle, comma, the sine of that angle. If my green's not fading too much. And in black, here's a point in the unit circle associated with this many radians, whose coordinates are a piece of cake. So humor me. The line segment I have in black right here, is this distance, is this length greater or smaller than the length of this line segment?
Should be the same.
It's the same because both of them are the chords on the same darn unit circle, subtending that same darn central angle whose measures in green, alpha minus beta. They have to be the same. Let me say it one more time. I meant to say the distance between these 2 points is equal to distance between these 2 points. Oh, but cheapers, you and I have in our back pocket a nifty little formula for computing the distance between 2 points in the Cartesian system. In the Cartesian coordinate plane, I think to compute distance between 2 points is as easy as looking at the square root of the sum of the squares, the differences in their x-coordinates, and their y-coordinates. And on the right-hand side of the equal sign, here too, I got the distance between 2 points in the Cartesian coordinate system. And so I think here too, I've got the square root of the sum, the squares, of the differences in their x coordinates and their y coordinates. Ah, shoot, that looks too sloppy. Can I number one, get rid of squares by squaring both sides? Number two, you guys allow me to come in here and expand those binomials. But I think that gives me this. The first one expanded is nothing more than cosine squared of alpha minus 2 cosine of alpha, cosine beta, plus cosine squared of beta. However, next, in expanding this binomial square, doesn't that give me, is it a plus sine squared of alpha? Minus 2 sine alpha, sine beta. And then lastly, is that a positive sine squared of beta? And even on the right-hand side, you guys, not too bad. On the right-hand side, expanding that binomial square, I think that gives me a cosine squared of this angle. Minus twice the product of these two beasts. Plus 1. Oh, I missed something, darn it. But it's easy. It's not really binomial, is it? I guess I'm merely left with a sine squared of that angle. Do you guys see why I'm using all my color? So let's see if I can skip a few steps. I think in green on the left-hand side I've got a 1. And in purple on the left-hand side I have a 1. But on the right-hand side in red I have a 1 by the Pythagorean identity, but another one in black. Don't they all cancel? I think I'm merely left with the black terms. And if you guys allow me with the black terms remaining standing, if I divide both sides by -2, doesn't that tell me the cosine of alpha minus beta is equal to the cosine of alpha cosine of beta plus sine of alpha sine of beta? And there is my subtraction angle identity for the cosine function. So did you see how, can you appreciate how lazy I am? I'm just looking at pretty pictures.
I so should have taken your trig class.
Well, in trigonometry, no, seriously, you should have seen everything derived out of thin air.
I saw sine, sine, same sign, or yeah. Cosine, cosine, sine, sine, opposite sign. That's as far as that went.
Oh, by the way, you guys, can you appreciate? Shoot, I failed to answer his question. I messed up. That's the addition angle I did. That's subtraction. I'll fix it. Watch. So again, x-axis, y-axis, here's the circle. Let's consider a point of view in a circle associated with t radians. Here are the coordinates. Given that t is fixed, would you guys not agree that p of added negative t is simply the same amount of rotation from the positive x-axis? It's just that I'm rotating in the clockwise direction. And again, shutting our minds down, not thinking, would you not agree that the coordinates are going to be the cosine of that angle, the sine of that angle? And t is arbitrary. I can tell you what the angle was. Because a t and negative t are so intimately related, do you guys not agree that this point right here is merely a projection of that point through the x-axis? Even though I'm sloppy. So I think these 2 points have the same x-coordinates. There's your even identity for the cosine function. I think these 2 points have opposite signs for y-coordinates because they're mirror images of each other about the x-axis. And so I think the sine of negative t is equal to the opposite sign of t. There's your odd identity for the sine function. And so I can finally answer his question. Watch. Look at the board. This really is my subtraction angle identity we derived. But to come up with the cosine of alpha plus beta, or x plus y, which is what he asked me to do, hold sheet, watch. Isn't that the same thing as the cosine of alpha minus negative beta? But since I just derived the subtraction angle identity, I'll apply it. Cosine of one angle minus another is the cosine of the first times the cosine of the second plus the sine of the first times the sine of the second. It's just that with the even angle identity for the cosine function, cosine of negative beta is positive, cosine of positive beta. But the sine of negative beta is a negative sine of positive beta. So I finally got around to deriving that identity. I just had to use my odd and even identities first.
So why can you switch out the negatives with the positives again?
You mean from here to here?
Yeah.
I didn't really switch out. I was more at Bradley employing this identity here. Namely that if you rotate negative t or positive t, I think these x coordinates, even though they're labeled differently, they have to be the same. I'm deviating from the positive y-axis along the positive x-axis. I think I misspoke. I'm deviating from the y-axis along the positive x-axis, same number of units. But in terms of y-coordinates, oh shoot, they're not the same, they're opposites. And that's what I exploited from the second line to the third line. Second and last line to the last line.
Okay.
That's why I emphasize students when they finish Math 30, please, you gotta go back and review your analytic trigonometry because it becomes so important this semester. Anything from the homework you guys? Yes, sir.
I have a 7.1 question.
Sure. Where are you at?
Problem 57.
57. 7157. Sorry, you guys, I didn't do a good job writing. The question really is this. Consider the function f that I just defined. Find the arc length for this function f in terms of x over the interval on the x-axis from here to here. So if you guys don't mind blindly, I'm going to come in. Can I erase this? Nobody minds. I'm going to come in and list my nifty little formula in my back pocket for arc length. To compute the arc length from alpha to beta, or a to b, excuse me, I've got the square root of 1 plus the derivative of f with respect to x twice. Let's just plug everything in. I think that leaves me with the integral from here to here of the square root of 1 plus something squared is just that when it comes to that darn something, is the derivative of the function f with respect to x. Which is
Root ln squared of t minus 1.
I can't hear you.
Ln squared of t minus 1.
Squared of.
Isn't that t? Oh, that's an x. That I can't read your writing.
Oh, thanks.
I'm sorry.
You're not using it yet.
Tell me that doesn't look like a t.
This is why typing is in, okay? Well, that's going to leave you. You guys, is that okay?
And you put a dt there too.
I should. These are t's.
But why is there an x up there? Oh, okay.
Ah, because that's the upper bound.
Okay, okay. Yeah,
equation.
no, I
It's
get
a big
it.
deal.
I get it. Yeah.
You guys got to be honest. Is that okay?
Yeah.
If you're not, I'll justify it. Sir.
Isn't that a f of x though, not f prime?
See, I disagree for this reason. Ooh, I can make room. Okay, you guys, I have my glasses off. I can't read it. Tell me what was inside the interval. Is it square root?
Root ln square root of t minus 1.
Got it. Now, using the fundamental theorem of calculus, isn't this going to evaluate to big F evaluated x minus big F evaluated e? Where big F is some function that's an antiderivative for what's in the integrand's position. Let me restate that. Big F has a quality that its derivative with respect to x is going to be nothing more than what's inside the integrand's position. Is that a square root? natural log square root of x minus 1. Would you guys agree? And if you do agree, then I think in differentiating f, that means I'm going to differentiate with respect to x, this integral. But that means I'm going to differentiate with respect to x, big F evaluated x, minus big F evaluated e. But that means term by term when I differentiate with respect to x, big F evaluated x, isn't that just this? Minus, well, differentiating f of v with respect to who cares what variables, aren't I going to get this? But that means big F prime of x is, oh, check this out. I guess I've got it sitting in front of me. That's just a square root of the natural log square root of x minus 1. Do you see how the differentiation process and the integral process, or shall I say, the differentiation process and the anti-differentiation process undo each other, and I'm merely left with what's in the integrand's position left over? Well, you got that variable of the bound of integration. I think the bottom bound of integration, the lower one, had no effect because, jeepers, I'm just differentiating a constant. Sir, do you believe me? Because to verify this, I merely employed that second fundamental of Fermi calculus.
Oh, I get differentiating and antiderivative. I was mostly confused about the bounds. So you were able to just discount the e in the end.
Yeah, I can because technically speaking, I was differentiating constantly. Notice the author was safe though. He started the bounds here too, at e as well. Because I think when t is equal to e, this becomes a 0 on the inside. The square root of 0 is just 0. Oh no! I never answered the question. Shoot! I guess that gives me, is that just simply this?
Well, you can simplify that.
Or this? Or this? And what do you get next? What do you get next? Come on, wake up. You get nothing? It's a horrible mistake, isn't it?
Mm-hmm.
You differentiate the natural log of x to get 1 over x, but the anti-differentiate natural log of x, oh no, I'm in trouble. What am I going to do? Yeah, I think so. Think about what I just said. You and I can easily differentiate natural log of x. We just don't know what its antiderivative is. To me, that just screams out. This is an application of integration by parts. Can I use this room? After all, I think with integration by parts, if I know how to differentiate something easily in the integrand's position, why not let u be equal to it? And dv be everything else. Because like I just said in English, I can differentiate it. Piece of cake. And by the way, with what's left over, I can anti-differentiate that. Still, piece of cake. I'll apply my integration by parts formula. I think that gives me my u times v, which in this case is x natural log of x, evaluated from here to here. Minus the integral involved in my v du, but that's just simply the integral of 1 with respect to x. Well, sorry, I meant from here to here. But that merely gives me an x. Natural log of x minus x, all of which is being evaluated from lower bound to upper bound of integration. Now it's just a math B game. I'm just going to evaluate. So that can be e cubed times 3 minus e cubed minus e plus e, which is 2e cubed, I think. If you double check my arithmetic. I hope this is.
Yep.
Your silence haunts me.
Why do you have to do parts for the...
Listen to the beauty of this in English. I think since you and I might kick our feet up, relax, don't think. To differentiate natural log of x is easy. It's just 1 over x. Oh, but shoot, look at the question. The question is, let's integrate it.
Yeah.
And a lot of times in my head, if I got a sole item in the integrand's position, I don't know how to anti-differentiate, but I know how to differentiate. That screams out at me. Place that thing I know how to differentiate in for you so that I can actually differentiate. And pay the consequences of everything else. And I'm hoping, I'm praying that the product of these two b's generates that second integral, which will be easy to integrate. Not that it's always going to happen. I'm just saying this technique is a good candidate. When what's in the integrand's position, you know how to differentiate, but don't know how to anti-differentiate. Anybody else? Sir.
From 7.1, can you do number 33? It's
Oh.
kind of the same, but I don't know, my answers don't match up.
Ooh, how nice. So we have an x squared, natural log of x. I'm sorry, sir, I lost it. What number is this?
33.
33. You guys don't write this down yet. I don't know if I've got the right balance. Nope, I messed up. It's this. Now, a lot of times when you have in the integrand's position, combination by division or multiplication, combination of both a transcendental function and an algebraic one, if you can't make a quick and easy use of to clean up the integrand's position, then integration by parts I think is a prime candidate as a technique for guiding integral. I sound goofy when I say that. I say prime candidate. You and I don't have that many techniques under our belt yet, but by the end of this week we will. For today, since it is the case that I can't conjure up a nice, clean, easy use sub to clean up the integrand's position, I guess I got no other choice. I've got to apply this only one other technique I have. I'll allow u to be something, and dv to be something else, and let's just give it a shot. I want a yes or no answer. Can you easily differentiate them? Yeah, I want an answer. Can you easily anti-differentiate them? I don't think so. I know I just did over there, but I still don't think it's very smooth. So I think I've got a wrong assignment for u's and v's. Oh, excuse me. I think I've misassigned for u and bv. In fact, I think I'd be so much better off allowing u to be a factor in the integrand's position that I can easily differentiate. And hopefully, what the heck is left over is something I can easily anti-differentiate. Oh, check that out. It really is. Let's commit to this assignment. Differentiate. Anti-differentiating. You know, I'm starting to like this. I could just casually see the product of v du in an integrand's position, identify that as an integrand I can anti-differentiate p sub k. Let's put it together. I think this integral is equal to the product of my u and v, evaluated from here to here, minus the integral of my v du, which is nothing more than this. And again, it is the case that I can anti-differentiate what's in that last integrand's position, 100% absolute piece of cake. And I'll evaluate from here to here. Now, numerically speaking, I do think that gives me a 1/3 e to the 6 times 2 minus a 1/9 e to the 6 minus my 0 plus 1/9. Oh, you guys, I don't know what that is. Is that a 2/3 e to the 6 minus 1/9 e to the 6 plus 1/9? Or shall I say, is that a 5/9 e to the 6 plus 1/9? Or shall I say 1/9 times e to the 6 plus 1?
5 e to the 6 plus 1?
Thank you. Did I lose my 5? Sorry about that. Did I talk too fast? Can you guys just give me a little feedback, please? Say something. Is this section just a boring piece of cake? It's so easy. You want to think about it, or is this killing you?
It's
So,
pretty
ooh,
easy.
There's a thumb up. It goes to sideways. A couple thumbs up. Yes.
It's VDU, right?
It is. It's VDU, which I have right here as 1/3 x cubed times 1 over x. But one of the x's canceled.
Oh,
And that's why I generate that x squared factor.
sorry.
Anybody else want to tack me on this? 39, same section? So 39. Just a graph. so 39.
Oh, I know that.
So everybody, I'm trying to sketch the graph of this function over the interval from 1 to e squared. So here's my x-axis. Here's my y-axis. Here's 1. Here's e squared. What do you think happens to the output of this function when x is equal to 1?
0.
Now, as x increases from 1 on up, I think graphically speaking, I'm going to do this, but am I going to come back up to this or not? Yeah, I think I'm wrong with the graph already. You know, I think when x is larger than 1, the natural log of something larger than 1 is positive. But again, if x is larger than 1, it too is positive. I think the graph is positive. I think it lives above the x-axis. Now, maybe I have problems with the curvature. But do this for me. Now that I think you believe me that the curve lives above the x-axis to the right of 1, then when x is equal to e squared, don't I just simply get this? Do you guys agree? And what happens in between? I don't know. I'm not sure. Let's just lie. Something like this. I am lying. Maybe do this. Maybe do this. How can I find out which? Differentiate, see if I'm increasing, decreasing, or change therein. Check the second derivative to look at concavity. When I concave down, concave up, maybe switch concavity. As x ranges from 1 to e squared. Well, I know, plotting points is no fun. That's so unsophisticated. I got a better idea. Bless you. Let's do this. Somebody panic. Just say something about what this result says.
As soon as it goes up, after it goes between.
Actually, you're right. I was hoping you wouldn't even go that far. I was hoping you'd say, there's only a critical number. And to the right of 1 over e, which is less than 1, I'm either strictly increasing or strictly decreasing. You just took it one step further. You said, well, if x is beyond 1 over e, clearly everything here is going to be positive. And so I think I'm strictly increasing. Well, I guess it means I don't do what this shape does. But I could do one of these two, which still doesn't answer my question. Because I think the solid curve and the dotted curve have different concavity. So let's check concavity. Well, at least over that interval. Check concavity is a piece of cake. Watch me. Use this version of the first derivative and differentiate it one more time. Don't I simply get this? And in the right-hand plane for any value of x, isn't this going to value to a positive number? Oh, shoot. What does that mean about the original function now? I said, oh, shoot. What does that mean about the original function? It's concave. Up. Therefore, I look more like the dotted curve, don't I? Debbie, did you see how lazy I was in making my decision just to get a clear picture? Not that you needed to. I was just simply looking at my derivatives. After all, the derivatives were not that bad to compute. I still think I'm going to be a little off. You know, at least I show an upward concavity. And you know what? I never read you the question, and I didn't read it myself. But her question was to sketch the graph of this region. But now the question is this. I can't. What number is this? 39? Look at the region bound by the graph of f and the x-axis over my interval from 1 to e squared. Suppose it's revolved about the x-axis. Let's compute the volume. So if I take this region, shaded in black, and revolve about the x-axis. Did I say x-axis or y-axis? I don't remember.